about 1 hour talk. And kind of I talk with Bruno what I will talk about, because the title was kind of everything. And Grothendieck, quantization. So, and he formulated kind of a precise question. So I will explain you Thomas result, plus its applications to polyvector fields and Batalin-Vilkavisky formulae. Just this is my point will be just to explain, to give a mathematically rigorous formulation of his theorem, what he really proved, and what are the applications of it. I will use language of operads. So sorry, this is just without. So let me kind of on Willwacher theorem and its applications to geometry. Some of its applications. There are more applications, I will talk about some of them. So let me first just start with a very general fact about Lie algebras, which of course you know. So assume you have a Lie algebra V. What does it mean? It means you have a representation of an operad of Lie algebras into the endomorphism operad of the vector space V. Therefore, there is a nice deformation. There is a general theorem. Whatever morphism of operads you have, there is immediately some differential graded Lie algebra which controls it. Right? Well, in fact, and moreover, even better, any morphism of operads is a Maurer-Ricartan element in some differential graded Lie algebra. So let me start with this. So because this will be then twisted. So general fact. Any morphism of operads, say operad 1, operad 2, is a Maurer-Ricartan element, in fact well defined in some Lie infinity algebra in general. We cannot assume its resolution will be quadratic or whatever. Maurer-Ricartan element in some Lie infinity algebra. So normally Maurer-Ricartan element is a kind of an infinite sum of terms. But good point, it's always okay, well defined. You have filtrations which always assure convergence. You don't need to assume anything. Therefore, in this case, what is it? You take just zero map. So you have nothing. You have a vector space, so you consider a zero map. You start with this. And then you apply this general machinery. Again, I refer to there are many important papers on this machinery. I think the first is van der Laan, a student of Sergei Merkulov.
What is that?
Deformation complex. It's a canonically defined deformation. I will explain you in Lie explicitly in a minute. So there is a canonical deformation complex. Then Kontsevich-Soybelin, but I dare you to read our paper with Bruno, because it explains several approaches. There are several approaches, whatever you like. Algebraic, or if you like the language of DG manifolds, or finds DG schemes. It's given even with examples. What is this DG? It's easy. So I would recommend you indeed, sorry, for this. I still look, it was written nice, even after so many years. Sorry again. Anyway, I often myself reread some parts when I forget. I want to refresh some facts. Okay, so what is this? This is a for zero maps it will be just a Lie algebra. So it will be a Lie algebra in general. And how to define it? Essentially, when you consider deformation complex, it's the same as you take resolution of Lie to Lie infinity, consider zero map to end of V. Now let me kind of change degrees. Kind of in homological algebra, instead of vector space V, we can work with vector space V1, which is kind of a graded vector space with shifted degree, so on. You can do similar on operads. So Lie infinity would have, it's a family, it's an operad which has n skew-symmetric inputs for any n of degree 2 minus n. But if I shift degree, say Lie 1, why I do it immediately? Because in polyvector fields, in the natural grading, Lie bracket has degree minus 1. Therefore, I need a grading where binary operation has degree 1, minus 1, not 0, if you look at here. So in Lie infinity 1, in fact, the operations will have degree 3 minus 2n. And this is very good. It's a configuration space. It's n points in complex plane modulo three-dimensional group. It's observation by Getter and Jones. Fundamental complex in this compactification is precisely this Lie infinity 1. So this is Getter-Jones. So this is a very good shifting. It has a deep geometric meaning. So what I claim, in fact, this is the same as fundamental chains of the compactification space of n complex points in the complex plane, Fulton-Macpherson. You take fundamental chains, big cells. Full will be Gerstenhaber, but this gives us anything. So let me just consider Lie 1. And then what is this deformation Lie algebra? As a vector space, this is just given by definition all S-equivariant maps from generators of this guy. But this guy has generators what? They are one-dimensional, they're now symmetric in this degree. So this is a one trivial representation of fundamental group with shift of degree to what? To home V tensor NV. Right? So we recover the standard Chevalier-Eilenberg complex. So this is a one-dimensional S module. Yeah. This is S. Okay, it's it's a direct sum for all n. Okay, let me Sn direct sum for n2 and higher.
I just can't read what's
Yes. That's that's home linear maps V tensor n to V. There is a permutation group X here, permutation group X here. So essentially, what I do, I symmetrize V to the n, but with shift degree. I recover precisely, this is what? This is Lie algebra, co-derivations of V shifted degree 1 co-algebra. Exactly it. So if you now read the rules, I mean, Lie bracket comes from the differentials, you recover this as a Lie algebra.
It's a product, not a sum. It's a product over n radian, not a sum.
Yes. Thank you. It's a completed thing, and it's infinite. You cannot assume it terminates. Of course, yes, thank you. So this is a co-derivation of this co-algebra. This is what is called Chevalier-Eilenberg complex of Lie algebra V. So we recover this immediately, and then we know any Maury-Cartan element here. So this is, of course, has a Lie bracket, right? This is just a differential Lie algebra. Any Martin bracket here is what? It's indeed Lie infinity structure in V. Indeed, this is just a definition of standard definition of Lie infinity. Co-differential, which this is it. I mean, yeah. So this is the solution of this equation is exactly Lie infinity structure in V. This is deformation theory of zero map. And if you now fix some particular map rho, what you do, you twist this Lie infinity structure by Maury-Cartan element. You get another Lie infinity structure. So this is kind of this association, this classical complex comes for zero map. So this is kind of Chevalier-Eilenberg relation. But if we come to here, so deformation complex of Lie 1, some non-trivial representation is a twisted, is a gamma twisted version, because rho is some gamma in fact. rho is some gamma. Rho is the same as gamma. It's representation. You can view them as identical. And then you can twist your Lie infinity structure by this element. You come here. Now, this is a general thing. Now we go to polyvector fields. And this is a story, in fact, due to Kontsevich, which I'm going to tell. He invented this. So what Kontsevich looked at? So Kontsevich graph complex. So really now we want to take, no, in general, let me start with any manifold. So let me consider global smooth functions. It's a ring. Let me consider its derivations. It's a module over smooth functions. It's infinity module. This is called tangent global smooth vector fields. It's C infinity module. It has always a Lie algebra structure. And Schouten observed long ago, now we know it's a general construction, but he observed that in fact you can extend the standard commutative derivations. We know derivations of any algebra give us another derivation. It extends in fact to the polyvector, to skew-symmetric algebra. And moreover, what is less evident, you can take tensor product over smooth functions. It doesn't matter because, I mean, in general, you would need maybe over numbers because derivations does not commute with module structure. But here, it's okay. Right. So you induce Schouten breaking. Again, what is non-trivial? It's in fact over this module. It quotients from tensor product over R to tensor product over as a C infinity module. This is a great observation. And therefore, this is our V. This is what I meant above. So this is our V with degree -1 and a natural grading. It will have degree -1. So this is my V. This is my V, and therefore, applying the above procedure, I have now deformation complex of what? Of Lie in degree 1 to endomorphism of polyvector fields on any manifold. Right? Endomorphism space of any manifold. Right. So let me come back for a second to, I mean, kind of 1 dashed, 1 plus. Let me make a comment to 1 above. Normally in deformation theory, so this is a complex in particular. So for a non-zero map, it's always a complex. It always has a differential. For zero, no, I mean, it's a Lie algebra. But once you deform a concrete map, you have a differential. And therefore, you can always think about what is cohomology of this row. Any cohomology, let me say. And often we were really interested in the cohomology 1, in degree 1. They give us infinitesimal deformations. Now in this case, it will be infinitesimal deformations of the Schouten bracket. Less attention was paid to H0. What is its meaning? Claim is H0 always classifies Lie infinity automorphism of your rho up to homotopy. So claim, a general claim. The zero cohomology of this deformation complex in general classifies, no, you have some non-trivial map. Well, maybe let me put here infinity. It could be Lie infinity structure, though we shall have Schouten bracket. So you have some Lie infinity structure. What is zero cohomology? The claim is this is precisely Lie infinity automorphisms of rho structure of rho Lie infinity of a particular Lie infinity structure coming from rho up to homotopy. So in fact, it's a set of homotopy classes of Lie infinity automorphism up to homotopy. Why is it so? Reason is very easy. Now we know. So now rho is some Mario Cartan element, right? Is MC element. Rho is MC element in this Lie algebra. So really now we have to look at this huge vector space co-derivations of this coalgebra. This is a Lie algebra. So rho gives a degree 1 element here. It's a degree 1 Mario Cartan element here. So let me denote it kind of a Chevalier-Ellenberg of V at rho. So it's a complex degree 1 MC element. And so it gives me a solution of this equation. But then if I have a very good weight filtration, so what I mean, I have a Lie algebra. Normally I want to define a kind of a what could be group associated to this Lie algebra, right? In general, it has no sense. It's infinite dimensional. You can do nothing. But assume that your Lie algebra, for example, is kind of a positively graded, have some weight filtration such that Lie bracket increase it. Then it makes sense to make it into a group. I mean, degree 0 elements to make into the group via this Campbell-Hausdorff formula. So essentially what I do, I took log of one element, another element, and this is some Lie series, and this is associative multiplication. Yes. Therefore, assume, in fact, in our situation on polyvector fields, we shall have this good filtration. We have no problem about kind of taking exponent of degree 0 elements in G. What I claim, it exists, just due to the weight filtration. But then, degree 0 elements here act on Mario Cartan elements, right? So given any degree 0 element, say H, then I can define a new one through adjoint action. Okay, sorry. It's a.
Could you just say that bit in the box again? So it's you're taking this big Lie algebra over there.
Yes.
And you're saying you can exponentiate.
Yes. Then I look at degree 0 element, the form of subalgebra. Degree 0. And then degree 0, I want to look, is there any group structure behind it? Can I define exponentiate? In general, you cannot, but if your Lie algebra is positively weighted, in fact, degree 0 elements, you can produce you can exponentiate. It's well defined. Look, I took a product. It's a completed Lie algebra. Then it's well defined. You have a completed group, formal group. Yeah, and this is our situation that we shall be able to do it. And look, we have this action. So in general, this is new. In general, if I have some element, I can act it by this gauge transformation and get a new one. But in fact, this gauge transformation is precisely Lie infinity morphism. So essentially, this is Lie infinity. Look at this case. What are the degree 0 elements? There's a precisely collection of operations. So degree 0 element H is what? That lies in home of V1 to V1, right? Of degree 0. So this precisely collection of operators of degree 1 minus n. It's a Lie infinity map. So kind of a generic element will give me from my original structure some new Lie infinity structure, but via some Lie infinity morphism. I want to study automorphisms. So now I want to assume output and input are the same. But look at the equation, what it is says. It's gamma plus commutator with gamma, plus gamma. Whatever you have, you always will have some term like this. Which tells you, in fact, that this is true if and only if commutator of h with gamma is 0. But this precisely differential, commutator with gamma is differential in the twisted Lie infinity algebra. Therefore, degree 0 elements, which are cycles, gives me automorphisms of my row. And then I can ask what is homotopy equivalence and get the exact term. So this is the claim. So this group, which often was ignored, this group classifies Lie infinity automorphisms. Now we come back to our example. This is what, Kontsevich was interested in H1. He was looking for abstractions. The answer for H1 is known, but now we want to classify exotic automorphism of polyvector fields up to homotopy. But in this formulation, the problem is undoable because a manifold is fixed. There is no hope to do it for any concrete. You can only think about stable limits, something like this, as usual. When you compute cohomologies, if you want to get a full answer, it should be some kind of stable limit, because then you can have extra classes. So Wilwacher theorem is not true in this setting. You have kind of to think what could be stable universal limit, something which you can get rid of M. So hopeless at this the question is now kind of the questions to behind Thomas' theorem is what is H naught of this algebra, of this complex? Sorry. This will be the set of all Lie infinity, it's like exotic Lie infinity, because they are non-trivial, homotopy non-trivial. Automorphism of Schouten brackets. But hopeless, you cannot do it. I mean, it seems this is a hopeless question at this particular moment in time. Right. So we should think about stable limits. So need kind of a universal. The word stable is not good because you cannot take a real direct limit of such things. But Thomas did it. I mean, he invented another graph complex and connected it with the Kontsevich one. It is his separate paper. So what universal? Right. So what I was talking up to this moment holds, in fact, for any Lie algebra, right? It just this question does not see particularities about that it's not an arbitrary Lie algebra, it's a Schouten bracket. So then the question comes. This is idea of Kontsevich comes. Let me formulate in the periodic terms. What means universal? Find an operad which really does not depend on any manifolds. Find an operad, say O, which has the property that means kind of a God-given representations in polyvector fields. It can see it, it's special. Such that there exists a kind of, it's God-given and unique. It's kind of a representation, so row canonical. From O to that one, to polyvector fields. And then what you can do, then you can study deformation complex of morphisms of Lie 1, of in fact even 0 morphisms, to this operad O. Kind of you put this O in between, sorry. This is unstable thing, and this becomes a stable version. So stable part, which does not depend on any choices. So this unstable bit of this, now I kind of want to split it in two. No, you can see, I mean, because of this, I mean, there will be a map. There will be a map, always a map, def from Lie infinity 1 to that kind of a still, it's in fact idea, we don't know it exists, to def of Lie infinity 1 and Tm for any m. Agreed? Because we have this, so we can always compose this arrow with another one to come here. So the question is, can we find it? The answer is yes, but it's strange. You have to assume M is affine. You have to fix a affine structure. I asked, we thought in Stockholm, is it possible to make this operad already deformorphism invariant? This O. You know, I use manifolds. And the answer seems to be kind of no. You have to do it first for M equals R, N, and then to use Fedosov techniques to globalize it. But still, it's an open question because simply we failed. Try maybe, so kind of fix a fine structure. I assume it right now. Fix a fine structure, and then we have it. But kind of you need a fine structure to define it. Maybe it has a deep meaning. Maybe this is just not a clever people look at the question.
Operad was not supposed to, it's supposed to depend on it.
Sorry?
So what do you mean? The operad doesn't depend on it?
Yeah, operad, I mean, this representation universal. This, yeah, it's only affine invariant.
The representation
Yes,
N is affine.
affine invariant only. It's not, it's bad, kind of. If you look at our setting, we should, but we don't have it. But still, later we shall fix it. So maybe it's a good question to think for people in the audience. Is it possible to modify, to find another operad already at this level? I don't know.
Which is a representation.
Yes, already. You have to yeah, already. So we tried to twist, so kind of you have to fix some affine connection to do it, and we tried to do it already at this level in Stockholm, but kind of we failed. Maybe it's our mistake. We didn't see it. But let us now give the definition. So this is idea of Kontsevich. This is what he called graph complex. He never thought like this. He never motivated like this. But this is essentially what he created. So in fact, his operad will be this. This will be Kontsevich. Thomas denotes full graph complex. True, because it's polyvector fields. Sorry, I mean, I will not use it. But this O, I don't know, I mean, who did it first? I thought I was in my paper 2 years ago, but then Thomas simultaneously 1 month later produced his one, and then I was put a reference on Lambrecht and others. So, but I knew nothing. I mean, I use it for some other reasons. On my paper on operads, configuration space, and quantization, where I simply gave it with examples, full details. So that's operad which Thomas denotes. So now, point 3, that magic operad O exists. So assume M is just a D for any D. Then the required this kind of a operad O exists, and is denoted by graph by Thomas. I forgot my notation. Essentially, this operad can be read again from Drum complex on. Okay, so
you need to fix the dimension.
huh?
You need to fix the dimension of the space.
Yeah, I mean, but again, the operad itself will not depend on any dimension. It will always have this canonical representation in any RD. Yeah, so kind of the operad is universal. It does not depend on M. On D as well. It does not depend on D, but since I started with some M, I have to specify what is affine space. D is arbitrary. So let me define this, and then so plan is, now I give you definition of this operad graph, and then I give you definition of that canonical representation from graph to endomorphism of polyvector fields in RD for any D. This is where D comes in. When you just want to represent it. But it in itself, it does not depend on it. And then deformation theory from Lie infinity to that magic operad gra is exactly what we need, and this is what Thomas studied. This is the motivation of this idea. We want to have stable limit of the problem, and this operad gives us it. It's universal. Right? So let me start with the definition. So definition 1. Consider first a space of graphs. So let, say, G and L be a set of graphs with n, so the continuality, so the set of graphs, so kind of this is a graphs, such that, so I, continuality of the set of vertices is n. And moreover, in fact, we enumerate them. We fix some map from this set of vertices to the set of 1 to n. So this notation in bracket, it means 1 to n. We fix it. They're labeled. Second, the set of edges is L. And moreover, we fix a total ordering of edges up to an even permutation. We call it orientation. So kind of we fix element in the not just linear span of this set, right? This is what we fix. It's else j's power. It's Q-symmetric else power of vector space spanned by edges. Yes, it's a line. We fix a basis element. There are essentially there are two.
Okay, that's what you said.
Yes.
You sort of picking an orientation.
Yeah. So I call it OR of gamma. It's orientation. And you know there are two orientations, this one and minus. I assume also it is unital element in line. Doesn't matter. So it's called orientation. So we fix it. Oh, this is it. Notice, I allow multiple edges. I allow loops. Anything is allowed. Graphs are not directed. There are no errors on edges. So, example. 1, 2 lies in G21, right? 2 vertices numbered 1H. Or this one is also good, 1, 2. And say I choose this H first, this is second, right? I should have to choose orientation. I don't show it, I assume often it's an element in G22, or that's what I will need in the BV story, version of this story, it's an element in G11, and so on. Next, definition 2. Now I define a collection GRA. This is a collection of Sn module, or full GRA. Oh no, simple GRA, sorry. That's what I'm saying. It's just a collection of Sn modules in the category of graded vector spaces. So each GRA n is a graded vector space. As follows. So I define GRA n to be the direct sum over all L0 and higher. And then what I do, I take, no, on graphs, as usual, there is a notion of a morphism and isomorphism on graphs. So I take linearization over K. So this is kind of a K generated by this set G and L. So N is fixed, but L is now variable. I shift degree to L. So each edge has degree minus 1. If there are L edges, graph will have degree minus L. So this means each edge has degree minus 1 in this picture. Modular relation. Remember, I have a graph with orientation. I assume that it's equal minus graph minus orientation. Essentially, it's a set of pairs, right? An element here is a pair, graph orientation. So I assume change of orientation, change in sign. Now, what it will do with my graphs? No, 1, 2 will be there, it's okay. But for example, this graph I have written above. Sorry. This graph is 0 in graph 2. Why? Oh, there is automorphism which swaps edges and reverses orientation. Therefore, it is equal to minus itself. So it is in fact equal, according to this rule, to minus itself. So, you know, I now take graphs up to isomorphism, therefore, to minus itself. Therefore, in the quotient, only those graphs survive which have no multiple edges. Okay? Therefore, so what is essentially kind of a morale? What is kind of a, so an element of graph N is again kind of is a graph with no multiple edges. Say 1, 2, 3, no multiple edges. There got that. And it will have degree minus 3, in fact, right? Now it's a graded vector space. Number of edges is degrees. Now I claim this is an operad. This is an operad. So I gave the definition. It's an operad, and then I will show you it will have a canonical representation here in any polyvector fields. On polyvector fields or on any affine space. You will see where we need affine structure. Claim gra is an operad. No, therefore, I take gra n, I take then the product over the field I'm working with gra m, and I have to need the composition for any I in n, right? I have to define a map to gra n plus m minus 1, which satisfies some axioms. No, let me just do it. So let me take gamma 1 here, gamma 2 here. So it's a graph, a directed graph with some number of edges and vertices, each edge at h degree minus 1, and remember this sign orientation. So they come with some orientations. So there is some orientation here, orientation 1 here, edges. Right, and I construct a graph, gamma 1 composed I gamma 2. So this will be sum of graphs with some orientation, which I will orientation will be just a product of this one. Say, I kind of consider now all elements, all edges. Nothing happens with edges. Edges will be preserved under the composition. Because look, I mean, fixing I simply fix some vertex in the graph. This is what I play with. I will play with vertices. Edges will be preserved. Therefore, if I have some ordering of edges here, ordering of edges here, then I kind of assume this comes first, this comes second, I have induced ordering. Right, so kind of ordering is, I have to explain what is gamma. And let me consider a subset, kind of gamma 1, gamma 2, in this set G. G will have n plus m minus n vertices, and if this graph has L1 edges, this graph has L2 edges, this gamma will have L1 plus 2 edges. As I said, I mean, they do not disappear. All graphs in this subset, let me define this subset, where this subset is a subset of this one consisting of all those graphs. Remember, graphs here, they will have n plus m minus 1 vertices, which satisfy the two conditions, such that condition A, consider full subgraph spanned by, so full subgraph I will just say spanned by vertices labeled, I fix I, labeled I plus 1 up to I plus here m, m minus 1, m vertices labeled like this. Full subgraph is gamma 2. Mean the full, I take all the edges between my vertices, forget all others, right? So if I specify the set of vertices, I consider all.
You just didn't need all.
No. No, let me just continue, then I give a picture. You will see the definition. So consider a full subgraph spanned by this vertex is in fact isomorphic to gamma 2. And second condition is, now we have a full subgraph spanned by this vertex. Let us contract it into a single vertex. Let me take my graph, take its quotient by gamma 2. Condition is, this is gamma 1. And I take this. This is the definition. And what it means kind of, let me give examples. It's essentially, I do the following. So I have my graph gamma 1. So this is some graphs with some vertices and say edges, right? Whatever. This is say ith edge. This is say. Then I take graph gamma 2. Again, this is something. Again, with vertices and edges. Then what I do? What is my operation? I raise vertex I. I mean, I've got all the edges coming to I, hanging in the air. I draw here this graph inside this huge vertex. And then what? I have a problem. I mean, my edge, I have some, and then I reconnect them. I take a sum of all possible reconnections. All of them say to this vertex, say 2 of them to this vertex, and the sum of all possibilities. And this is exactly what I have written here. I always get a subgraph spanned by this will be fixed gamma 2. And when I contract it, I get my original one.
Isn't this exactly the Kreimer-Hopf, the pre-Lie algebra graphs you defined 25 years ago?
Yeah. But this is operads structure. This is not a Hopf product.
No, but he used this to
Oh,
construct
yes, yes, yes.
3D structure. So
Yes, yes. It's a similar definition of Hopf algebra non-graphs. But yes, I mean, essentially this is it. Yeah. So, but again, for me, this is operatic composition. Yeah, so essentially, right, you can always go the other way around. From gamma, you produce a sum over these gamma 1s, gamma 2s, gamma quotient, gamma.
Yeah, but actually, he
Yeah.
first defined it the way around you've written it, but he inserted in all vertices.
Yeah, yeah.
So that's how it comes in quantum field theory. So that's fine.
But one has to check.
No,
So crime is fine. You insert, yeah. So you don't fix one value. You do sum over all. It's the same.
One has to check that it goes to the quotient by this orientation.
sorry?
The vector space gra n is a quotient of the free
Yes,
space on graph by this orientation shift.
yes.
So it needs to be checked that it works. It's not.
No, it's okay. I mean, nothing happens with my edges. You know, I mean.
Well, you can have multiple edges, but the
Yeah.
gamma 1 and they disappear in the when you glue something inside. So there's a check to be made. It works, but
No, but you cannot. If you don't have multiple edges, you will never produce multiple edges in this. I mean, whatever produce, they will get dead. So I think it's. Okay, this is. No, maybe. Sorry, I mean, but.
It's clear if you've got multiple edges in the one you insert in the middle, you have multiple edges in the other.
Yeah, in the same. I mean, yeah, and
Multiple edges in the one you're inserting into.
Yeah.
The question, isn't it?
yeah, but I mean, no.
Create new
What is correct? If you have a multiple edges before, you can split them later. They can contribute, and therefore it will violate the rule. But kind of if we assume right from the beginning they are not there, no, we can assume that in fact we take graphs with no multiple edges. Then this is it. This is a clean definition.
So you're not
No
really
problem.
forming a quotient.
Right. Right. So as I told you, the idea was that now the main why we need this opera, just because of its beautiful property. It has a God-given representation on polyvector fields provided we fix affine structure. Maybe, I mean, this condition about affine structure can be waived. Kind of one can construct, one can kind of do this globalization already at this level. So it's a big problem, I mean, because globalization was done at the Kontsevich complex level. Can it be done at the operette level? I don't know. We failed to do it. It's not quite. So next point in this story that this opera admits a representation. There exists kind of a God-given representation from Gra to the endomorphism operand of polyvector fields on any affine space. So first let me reinterpret this algebra to construct this operation. So what are polyvector fields? Now in RD, it's affine space, therefore you have the usual coordinates.
Sorry,
Right.
so your previous remark was to have this claim with RD replaced by an arbitrary manifold? That was your...
Yes,
That's your
can
claim?
it be done? So kind of I will use now operator delta, but now assume you have a fine connection in RD. Can you twist representation so that operatic compositions holds true? You know why it's important? Because then all other globalization theorems are not necessary. You can forget, I mean, every time whatever you do this graph copy, you need to check globalization. But it all comes in fact from this particular representation. This is where applications come. If you can do it at this level, it's kind of a universal globalization of all the applications. You don't need to check it anymore. It's an open question. It's a good question, but I mean, is it possible? Kind of, I don't know. So let me explain. So kind of, okay, assume you fix a fine connection. Can you do it for now for M? This is the open question. You can do it for kind of homotopy representation of an operad. But what about genuine? This is what we may remark.
Have you thought about this kind of similar question for people in equivalent quantization? They had some solutions to this similar question, and they used some Boardman approach using some universal bundles and universal connections. I don't know exactly the details, but I mean.
No, we tried universal bundles, but we failed.
But did you?
But not what you mentioned. I never saw. It's interesting. Maybe it will work.
I just suggest
Maybe you will have a look at that. And just look at this program if you read these papers. Why not?
But I know that in Luxembourg, for example, Ponsin knows these techniques very well.
Good, but we tried as usual. We took Fedosov resolution on any manifold. We try kind of, you have the representations, vertical representation, and as usual, you want to choose a section consistently. But we've got abstractions. But, sorry, I mean, it was maybe 2 years or 3 years ago. Memory was,
It's
not,
it can't be done.
yeah, we have not done anything, but we made an attempt.
I've been able to do it. So.
Yeah, but it's a good question still. It cannot be globalized. So let me see. So ID has coordinates. Let me introduce formal variables of degree 1. And consider kind of a algebra. I can consider now kind of a smooth functions in XD and kind of polynomial functions of these anti-commuting variables. This graded commutative algebra. So let me denote it this kind of a by ORD. Okay, I have too many O. No, essentially these are precisely polyvector fields as an associative algebra. As a graded associative algebra, this is it. And on this guy, you can introduce an operator which is unfortunately only a fine invariant. It's a second order differential operator. Second order operator with respect to multiplication to D, right? It's second derivative sum over xi psi y. This operator has degree -1. And then in fact, Scouten bracket of two polyvector fields f and g is just the usual. It's like in BV formal, whatever you have. It's minus degree of f, delta, you multiply minus degree of f, delta f applied to g, minus f, delta applied. So this is what a Scouten bracket is. But I mean, Scouten bracket is diffeomorphism invariant. But this operator, unfortunately, is just. And now it's clear how you represent it. So now I need to define a map from gra n to home of, I take nth tensor power in this representation of ID. So from any graph, say with n vertices, say L edges, right? I have to produce a map, an element in here with n polyvector fields inputs, one polyvector field output, right? So kind of phi gamma is what? Yeah, it's a map. So it's so kind of I have say gamma 1. It's n polyvector fields. Okay, and maybe I should not use gammas. Say dn, and I produce some phi gamma out of them, of this n polyvector field. So these are V are elements in the polyvector field. So I need to produce a differential operator from any graph, a map, universal map on polyvector fields, and I produce it as follows. So phi gamma applied to V1, Vn works as follows. You take tensor product of these Vn's. Yeah? Then you take a wedge product over all edges in the graph of operators delta E applied to this tensor product. This will be, I will explain you what is delta E. This will be an element in the nth tensor, still in the nth tensor power of polyvector fields. sum of terms. And then you simply apply operation mu. Here you have, you simply multiply, you use multiplication in polyvector field. So mu is a multiplication.
What is nabla e here?
I will define it. Let me just simply start with mu. So assume this, I just tell you the following. So assume I have this operation on Vn, which produces me another linear combination of such tensor products. I will explain you. So it will be now a sum of such tensor products. I have an element here. And then mu will be just a usual multiplication. So if I have now A1, AN here, I just multiply them at the end. This is mu. So mu is easy.
It's the wedge multiplication. It's the wedge multiplication.
Yes, yeah. So, no, for me, wedge is just multiplication of these monomials, so I don't write them. So let me define what is delta E. And now you will see why we need this operatic composition. What is this operatic composition? This is Leibniz rule. When you apply operator of nth order, of k order to a function, to a product of functions, you just distribute in all possible way. This is what this rule is. You hit all this in all possible. This is Leibniz rule. This is why it works. I mean, this is why it is a representation. Okay, it's already 1 hour. Shall we have a break or continue for some 10-15 minutes? Whatever you prefer. I mean.
It's about
Let's
time.
finish that story.
Finish.
Too nice.
Let me finish this story that at least I give you definition of this operator, and then Kontsevich graph complex comes in. Okay, right, thank you. So let me finish this story. The definition is the following. So what is delta E? Now remember, I have some graph, say this one. All vertices are labeled, right? So this graph should be produce me an operator from arbitrary 4 tuple of polyvector fields. Oh, sorry, again, it's V. Now, therefore, to each vertex I now associate my polyvector field. Right? To each vertex I associate my input polyvector field. Therefore, each edge, in fact, is what? Each edge gives me 2 elements in here. So assume I have an edge of this type, I, J. It connects vertex labeled by I to vertex labeled by J. Therefore, here I have Vi, somewhere I is placed in this product. Here I have Vj, some place in that product, and then I define delta E as an operator. It's a sum. I apply xi derivative to the i's Vi, then the product psi I apply to Vj, plus I swap. Okay, I have bet. It's kind of a I. Let me summation put alpha. I apologize. This applies again to V1, then the product xi to Vj. So EI would act, so say the edge 1, 2 will act on this pair in this way. The edge V and V3 will act on this pair in this way. And I take a sum. Remember, operators have degree -1, so I have to choose an ordering of edges. This is why I have chosen orientation. So it's a well-defined operator. And you see what happens with the edge. Simply, every edge means either dx or d psi. It's a partial derivative. And then Leibniz rule tells you that the map is indeed a representation of composition in Gra and composition on polyvector. Of morphism of such operators is the same. They commute. So this proves the claim. Right, so this explains the formula and proves essentially it's the claim. Therefore, let me summarize. We have a canonical operad gra. So we want to study again deformation complex of Schouten bracket, but we found intermediate operad gra, which has a universal representation in polyvector fields for any D. As I told you, deformation theory of this composition is hopeless. But here we know all these seeds, whatever D. Here we have all these seeds, a canonical DG Lie subalgebra, which is kind of universal.
Sorry, I cannot see in your formula here. I cannot see the structure of the graph because apparently there's just you just enumerate the edges, but you don't see the.
But what is the graph? It's just collection of points and pairings. This is exactly.
Yeah, but how do you know?
This is all I need. I have a collection of vertices 9, and I have pairings. Delta E defines a pairing, a choice of I apply my operator. So from this formula, I can read my graph back.
So you don't change it really applies to the I and J
No.
guys.
So once I fix which pairs I apply my operator, I can reconstruct my graph. I simply write each such pairing in this way. This is one-to-one.
I'm sorry, I'm confused. Could you explain again delta E? I'm sorry, I'm lost. So we have V1.
I have to explain what is.
We take one E. So E is the edge from I
Yeah.
to J. Okay. And then what is delta E on V1, V2, V3, V4? Can you just say it again?
Okay, let me just say let me take this gamma, right?
Yeah, this one.
What is phi gamma
Yeah.
of this guy? So it should be an operator on all possible pairs of polyvector fields. Let me tell. So this will be some multiplication applied. I have just one edge E applied to this V1 tensor V2. And I use this rule. So this is now multiplication applied to what? I apply dv1 dx alpha tensor product dv2 d psi alpha plus dv2 d psi alpha tensor dv1 dv2 dx alpha.
Okay.
And then I multiply. Essentially, I delete tensor product, right product. You see, this is exactly Schouten bracket.
Yeah, yes, sure.
And I can do it for any operation.
We see that.
So let me summarize. We got a problem which may be not hopeless, but it seemed hopeless yet for many years before Thomas did it. But at least we've got this universal thing, stable. We can now forget about any particular polyvector dimension. As I told you, it's undoable, but we've got it, and I will talk about it after some break. Maybe for another 20 minutes.
So at some point we should say something about the differential in graph cohomology.
Yes, I will now do it. Because differentials will come from representation to graph. I have yet to explain. Okay, you know what I have done. I have explained you this arrow, but I haven't yet defined this one, right? This is also it's not zero. It's non-trivial. I will do it. And this arrow will give us differential.
The GR is not a DG opera.
Gra is not. It's just a usual opera.
What is confusing is
wait,
Koncevich
it's
graph
not-
complex.
No.
It is
So
not
Gra
the
is
paper
not.
in 93. Maybe you're confused, but when people say Koncevich graph complex, it's the
Okay,
paper in
so it's a-
93.
No. I defined this one, and now I explain you this arrow.
Yeah,
Next, I will define you a map of these two operas,
yeah.
and then I will construct a now real complex from the map I have not yet defined. This map will give me differential in the graph complex. I will give explicit formulas.
Wait, so there is a differential in the graph complex at the
Later, yes, it will be differential in the graph complex, but Gra is an operand. It's not differential.
An operand in graded vector spaces.
Yes, it's a operand in the category of graded vector spaces, not complexes. No differential in graph.
And I just say again, it's not the graph complex, the commutative graph complex of Koncevich. It's not these ones. Because he put orientations on the edges, so we could not have loops like this. These are not the same as.
Yeah, no, there's several variants. There are
Exactly.
Yeah, several.
You know.
Let me say the following. In fact, let me say the following. That's in his first papers, he defined this graph complex has an even version. This particular graph complex is designed for Skeleton bracket of degree -1. So there are other graph complexes where, I mean, you have to choose an error on it. You have to choose an error on it. And then you have to quotient by. It's a different graph complex, so it's a very different one. I mean, there are many graph complexes of Kontsevich, many of them. And this graph complex is, in fact, Kontsevich never called him graph complex. He simply, I mean, he introduced them in the paper just before he proved formality theorem. He tried to look at the kind of universal abstractions to deformation quantizations. He tried, in fact, to look at the degree 1 cohomology classes here, found nothing, but found degree 0 class, which is exotic automorphism. Tetrahedron. I will explain tetrahedron graph. This he saw many years ago.
Can I ask a quick question here? I mean, what you said is that thing you started with there, lambda dot TRD, that's a Gerstenhaber algebra.
Yes.
Right? And now you say you've got a BV structure on that Gerstenhaber algebra.
Yes.
And then your GRA acts on that through the BV structure. Is that true in general? Right?
No, for general graph, I mean.
For general Gerstenhaber algebra.
No, you cannot, because
Graph
graph has very special operatic compositions, which is essentially Leibniz rule. Therefore, your delta always must have kind of on these two inputs.
All you used was that property there, right?
Yes, for this formula it's general.
All you used was the relation between the bracket and the delta.
No. I use this one. That, I mean, you know, my delta acts as dig xi partial derivatives on one vertex as a partial derivatives on another. And then.
So you're telling me it's not just a consequence of the formula?
No.
Identity.
It's just consequence of this formula. I need a particular formula for delta for this to work.
So if you choose a different BV operator,
It plays no.
you stick with RD with its Gerstenhaber algebra structure, but choose a different BV
Yeah.
operator.
Let me say, answer. For general delta, I still can define this operator. What is not true, I cannot then say that operatic composition in graph will transform into operatic composition of such operators, because delta could violate it, general delta. But for special class of delta, it works. Operators make sense always.
It's not really a BV operator. It's an accident.
Yes.
The BV operator. That's not relevant to your computations. Is that what you're telling me there?
No, I'm telling you that its explicit form is crucial for this to work. I cannot just say, let me have something which is second order. It makes sense to define this phi gamma for any graph, but it will not be representation. If I compose my graph, I have to have a composition of psi gammas. And for general delta, it does not follow.
Okay, I believe you. I can't see it, but I believe you. I know it's delta.
So how long is the break now? Or? We're taking a break, right?
10, 15 minutes?
Okay.
Let's do something.
Peut-être que